Okay, so this is the last video for this course in functional analysis and spectral theory, and I wanted to finish the course with a fairly recent theorem. It's due to Vladimir Mueller and Mueller-Tomilov in 2007, and it extends the Blue-Monson theorem from Hilbert spaces to little LP spaces, and that's a good example to show that extending results from Hilbert spaces to, say, reflexive Banach spaces is not just a matter of routine application of the techniques of the course. Of course, the techniques of the course are critical, but sometimes you need a lot more than that to understand how to do things in general Banach spaces. Now here, what we'll see is that Mueller and Tomilov managed to exploit the fact that little LP has an unconditional basis and the properties of that basis to mimic the almost orthogonality argument in the proof of the Blue-Monson theorem. Let's have a look at how this works. Okay, so first of all, the easy direction is just as in the Hilbert space case. So I won't redo it. You can just literally copy the proof. Now, going into the hard direction, we will once again define alpha to be the limit of the Tn of x, which we know exists as n goes to infinity, because this is also the infimum of the Tnx, because this sequence is non-increasing, the limit of these quantities. And again, without loss of generality, we're going to assume that alpha is 1. If not, we renormalize the x. Now, again, just like in the Hilbert space case, I can give myself an epsilon, and I can pick an m in n, such that for all m, little m greater than m, Tm of x in the norm of my Banach space x is smaller than 1 plus epsilon. That's similar to what we did in the Hilbert space situation. Now I can do something more that's really exploiting the fact that I have a canonical basis to little LP. So I know that the component of TMX in that basis have to go to 0. So if I denote the canonical basis of little LP by En, right, that is to say En is the sequence that is 0 for every values of j except when j is n, in which case it's 1, and I denote by Pn the corresponding partial sum projection. Projections. Right, that is to say that Pn of a sequence yj is the sequence that is zjn with zj equal yj if j is smaller than n, and zj equals 0 if j is above n. Right, so having defined that for any n in n, I can say that if I pick a capital N large enough, I'm going to pick n such that away from the first capital N term, T capital M of x is small. Right, and I can do that because Tm of x, that's a sequence in little LP, and if your coefficients are little LP summable, then they all have to be small after a certain time capital N, right? You have to tend to 0 if you're going to be summable. So I'm picking a capital M first, that has been done here, based on epsilon, so you give myself an epsilon, then I pick an m such that this holds, and then I pick an n, which of course is going to depend on capital M, such that this holds. Right, so that's happened first, and that happened second. Okay, and epsilon was set up at this moment. Now, the third thing I do is that I pick a k in n, such that for all k, little k greater than k, P capital N, and capital N has been fixed, of Tm plus k of x. Okay, what is that? It is the sum let's say raised to the p, it is the sum from little l equal 0 to capital N of Tm plus k of x tested on the dual functional EL star, right? That gives me the else component of the sequence Tmk plus x, which is a sequence in little lp, and that's raised to the power p. That's by definition of the LP norm. Now I can make that smaller than epsilon, right? Because Tm plus k x EL star does go to 0 as k goes to infinity for all L in 0n by assumption, because my orbits are weakly converging to 0. So this here, pick capital K such that this holds, is really the analog of the almost orthogonality argument. I'm going to say that, I have the terms that are on the first capital N component on my sequence and the first that are on the other parts of the sequence, and really there cannot be much of the norm left on the N term if I look far enough. So this is going to be the appropriate replacement of the almost orthogonality, exploiting the weak convergence to 0 of the orbits. So I want to exploit these three things together. Let's start using color here because it gets complicated. So this is property 1, this is property 2, and I'm going to call that property 3. Now, there's some tricky numerology coming up. Okay, here it comes. So you let delta be a positive number. This is the number that's going to get arbitrarily small eventually, not the epsilon. Epsilon is going to be something fixed based on delta. Now you pick t, a natural number, such that t to the minus 1 upon p prime, the conjugate exponent of p, is smaller than delta. And then you choose, you have to remember that this is chosen at that moment, epsilon greater than 0. Epsilon, actually, I'm going to take it definitely smaller than 1. So epsilon in 0, 1, based on that t, which is itself based on that delta, such that for every s between 0 and t, I have the following crazy estimate. 1 plus epsilon to the p plus 2 to the p times s raised to the power 1 upon p plus s plus 1 times epsilon is smaller or equal than 2 s plus 1 times 1 upon p. Okay, and I'm going to call that box because that is a black box. It's very mysterious why you do such a thing. Of course, that's not the way one designs a proof. You have this intuition coming from 1, 2, and 3 that we've picked before, and then you start to exploit that intuition and see how close you can get to the almost orthogonality idea of Hilbert spaces using that. And at the end, you will see that there is a certain constraint between a whole lot of parameters in terms of how far apart in the sequence you have to be to have something that's close enough to orthogonality, using the decomposition into the first capital N elements of the basis. And in order to make things work, you pick up an inequality like this crazy one in the box, and then you have to convince yourself that this constraint is not something that's impossible to realize. Now, of course, here it is, because you just see what happened as you send epsilon to 0. Then you really just getting that 2 times s to the 1 upon p is smaller than 2 times s plus 1 to the 1 upon p, which is true. So by choosing, by continuity and choosing your epsilon small enough, you can make that happen. Okay, so let's keep it as it is. And what we're going to do now, having fixed all of these parameters in this way, is we're going to prove the following claim. So the claim is as follows. For every s in the interval 1 to t minus 1, Okay, you have the following, and the following claim, we'll call it PS, we'll prove it by induction, is that for every mj increasing sequence of natural numbers, if you have that m1 is far enough and the distance between two elements in that sequence is at least k, so that's the idea of being far down the track enough and looking at separate enough powers. So if you have that for all j's up to s, then, so these two things, well, imply, I should say, so this condition imply that the sum from j equal 1 to s of the t mj of x in norm has to be smaller than 2 to the s to the 1 upon p. Okay, so we'll prove that by induction. Okay, so let's start with s equal 1. So for p1, okay, that's very simple because my only possible sequence is the constant sequence, was just the term m1, and then I have to look at tm1 of x. And what can I say about tm1 of x? Well, I can say that this is smaller than 1 plus epsilon because m1 is above capital M, and epsilon has been chosen between 0 and 1, so this is certainly smaller than 2, and 2 is certainly smaller than 2s to the 1 upon p, because s is 1. Okay, so that proves p1. Now I assume ps, and then we're going to have a look at ps plus 1. So I need to pick a sequence, increasing sequence, that is such that little m1 is above capital M and mj plus 1 minus mj is above capital K for all j equal 1 to s plus 1. And then I start computing the sum j equal 1 to s plus 1 of my tmj of x. And then I use an idea that's reminiscent of what we've done in the Hilbert space case, right? I factor out, what is it, t capital M minus m1, yep, that's a positive factor, and then I get the sum j equal 1 to s plus 1 of t mj plus m1, sorry, that's the other way around, minus m1 plus capital M of x. Right, now I have a contraction, so I can split these things, and now the point is that I start my entire sum at t capital M. So this is smaller than t capital M of x plus the sum j equal 2 to s plus 1 of t mj minus m1 plus capital M of x. Okay. Now what I'm going to do next is I'm going to split things into the first capital N component in the canonical basis of little LP and the next components, the ones from capital N plus 1 to infinity. And then I'm going to use triangle inequality. So here, let's say I've got the term that is multiplied by Pn. Here I'm going to put a term multiplied by 1 minus Pn. And then by triangle inequality, I'm going to split the term that is 1 minus Pn in front of the Tm, and the term that is Pn in front of that sum. Okay, now this is the hard term. Let's worry about it in a minute. This term here, we know already is smaller than epsilon because that's the way our capital N and our capital M were chosen in the first place. Here, everything is above capital M. So we know that when we take Pn of that, these terms in norm are also all smaller than epsilon. this is by condition 3. So using 2 and 3, we get, well, let's keep the first term as it is. And then the second term smaller than epsilon. And well, in that last term, we have s elements, and they're all smaller than epsilon. So we get plus epsilon plus s epsilon. But now, the key thing in the first term is that these things, that's a sequence that only has component up to the capital Nth term, and that's a sequence that is 0 in the first capital N term. So this sequence and that sequence have disjoint support. So now we use a very specific property of that basis and a very specific of the LP, little LP norm. We use this fact that when we have a sum like that of things with disjoint support, their LP norm is really the LP norm of this raised to the power p plus the LP norm of that raised to the power p and then you take that to the 1 upon p. Okay, now property 1 tells me that the first term is smaller than 1 plus epsilon. And what do I do about the second term? Well, there's not much I can do, but what I can do is that I can apply the induction assumption. And the induction assumption will exactly tell me, because there's only s term in this sum, right, from 2 to s plus 1, that the second term is smaller than 2s to the 1 upon p. And then that get raised to the power p, and then the whole thing get raised to the power 1 upon p, plus s plus 1 epsilon. Now I'm staring at this, and I really want it to be smaller than 2s plus 1 to the p, and this is the case, well, because of what we've got in the box. Our epsilon was chosen precisely to guarantee that this would be smaller than 2s plus 1 to the p, and that proves the claim by induction. Okay, now to conclude the proof, let's take a subsequence. So let's take nj, n to the n, increasing, and then given delta, I'm picking epsilon, capital M, capital N, T, and capital K as above, and then I'm gonna choose n prime in n such that n prime is greater than m plus k times t. Okay, I can do that. So m and k and t are all determined by delta, and then my n prime gets determined as a function of delta in that following way. Now I want to write this n prime as, well, it is of the form m plus k times t, so I'm going to write it as m plus little m times t plus some rest for some m that is above k and some r that is, well, that is the rest, so that is between 0 and t minus 1. Okay, now let us also notice that for all j that is between m plus little r and n prime, we have that there exists an L that is between 0 and m, and there exists a L prime that is between 0 and t minus 1, such that, you can rewrite your j as m plus little r, so L primes times m, some multiple up to t, plus a little l. That's right, between 0 and m. So you can write every j in that way, and then decomposing in that way, when you look at the sum that we want to estimate, j equal 1 to n prime of t and j of x, you can cut it into, well, the sum of the first few terms, so up to m plus r, and then you have t and jx, and then the sums after. So after that, you've got a sum L equals 0 to m, and then let's keep inside the sum L prime equals 0 to t minus 1 of t n. So I've rewritten my j in that particular way. So m plus r plus L prime little m plus L applied to x. Okay, so the first term is no big deal. The first term is smaller than m plus r divided by n prime times x. As I send n prime to infinity, this is going to go to 0. For the second term, that's where I want to use the claim. So I have a plus little m plus 1 divided by n prime. And what does the claim tell me about such a thing? Because I have an appropriate increasing sequence, the claim tells me that this is smaller than 2 times t to the 1 upon p. My little m is smaller than n prime divided by t. So this entire thing here is smaller than m plus r divided by n prime multiplied by norm of x plus, because I've got m plus 1 and not m, let's just control that by 2m. So plus 4 times t to the 1 upon p minus 1, right? Because my little m, let's have a look at this, right? N prime is of that form. So my little m is smaller than, has to be smaller than n prime divided by t. Okay, and 1 upon p minus 1 is 1 upon p prime. So this entire thing here, because of the way my t was chosen, is smaller than m plus r over n prime times norm of x plus 4 delta. Okay, all right, because this is minus, this number here is minus 1 to the 1 upon p prime. So by taking my t large enough, I've made that small, and small in the sense of delta. Now you send n prime to infinity, and as n prime goes to infinity, this goes to 4 delta, and delta was arbitrary. And that concludes the proof of Mueller-Tomilov theorem about extension of Bloom-Hansen to little LP spaces. And you can tell that what we've fundamentally exploited here is the fact that the canonical basis of little LP is very nice and allows us to compute norm by exploiting disjointness of support. This is what we've done here, and that allowed us to disentangle different behavior of the powers in a way that is similar to what we did when we exploited the almost orthogonality, and then that allowed us to exploit the weak convergence of the orbits to 0 only on finitely many terms of the sequence. Okay, and this concludes this video, and this concludes the course.